This is the first of a two-day lesson on binomial expansion. So we've now completed the arithmetic sequence lesson, the geometric sequence. We've learned about series, both arithmetic and geometric. With that, we've learned about sigma notation. We've learned about how geometric series can be finite or can be infinite in some cases when they approach a number, okay, when it's a convergent geometric series. So today we're going to turn our attention to something called the binomial expansion and Pascal's triangle. This is a two-day lesson. Today's lesson does not include this homework handout that's in your packet. It's that homework handout, homework number 5, is going to be for tomorrow's lesson. Today you're going to have some problems from our lesson to post to Google Classroom. So here we go. So first of all, Pascal's triangle. And this thing starts here. This is this handout that we're using says Pascal's triangle is a pattern of numbers that was discovered in the 17th century. And I want to say, wait a minute. Whoa. What do you mean discovered in the 17th century? It was not discovered in the 17th century. There was a Persian mathematician. I do not know how to pronounce this name, but there was a Persian mathematician in 200 before the Common Era. Some people call that BC. But in mathematics we call that the before the Common Era. So 200 years before the Common Era, the numbering that we use, there was a mathematician who was studying this pattern that we now call Pascal's triangle. But a little bit after that, in the 10th and 11th century, which was about 1,200 years later, there were two different mathematicians, one from China. Again, I'm sorry, but I don't know how to pronounce the name, so I'm not going to mispronounce it. But this name right here, in China, this mathematician, absolutely we have evidence of studying the same pattern. And also, again, in Persia, another mathematician, Al-Qajari, was studying this pattern. And then in China, it's sometimes called Yankees triangle, from a mathematician with the same name in the 13th century, so 1200s, and as well as in Persia and India area, Khayyam's triangle, named after the poet, who was also a mathematician, Omar Khayyam, if you've ever heard of his poetry. But he is attributed with also studying this triangle, this pattern of numbers. Blaise Pascal, who has the name attributed to this triangle, he wasn't even born until 1623, and it was in 1654 that the work was published. So he did not discover this triangle, but what he did do is he was influential in popularizing it. He used it in probability theory, mostly because he and his father both loved to gamble, and using this pattern of numbers was one of the ways you could look at probability of certain events occurring. And so he used this pattern in probability theory. So we're going to change, because this was like 2,000 years after our first evidence of someone who was studying this pattern is when Blaise Pascal published it. So instead of saying here where it says that he discovered it, no. He popularized this pattern, and so that's where his name is attributed to it. And here's how this pattern goes. We've got this triangle, and we call it row 0. And in row 0, there is just one element, and that is the number 1. In row 1, the next, which is actually the second row, but we call it row 1, there are 2 elements, both of those are 1. Then in row 2, we have elements 1, 2, 1. Well, where did that come from? The sides are always 1s. The first element in each row is always a 1, and the last element in each row is always a 1. The other elements come from adding the 2 above it. So I'm going to add 1 plus 1 to get 2. Now when we go on to the next row, we start with a 1, but to get to this next element, we would have added the two terms, 1 and 2, that are directly above it. 1 plus 2 gets us 3. And then this other one is 2 plus 1 gets us 3. So, and that right there is row 3. If we go to row 4, well, we know that it's going to start with a 1 and end with a 1, but what are the other numbers? Well, you just add the two that are together and write it down below in each one of those. And then each preceding row, we do the same thing. I want you to add yet one more row to go to row 6. And I want you to fill in all of those boxes following the pattern. So you might need to pause the video and fill them in to complete all the way to row 6. Again, you get to add an extra row. I want you to do that. Okay, hopefully you've paused it and you've filled this in. There will be another row down at the bottom here. And to check your work, those are the answers that you should have in this triangle, which we call Pascal's triangle. Okay, so this can continue on forever and ever. We could keep going and going more and more and more rows to do this pattern. There's a lot of super fascinating things about the patterns here, not only about how this triangle is created, but what happens when you add each row straight across. What happens? Like there's numbers, there's a pattern of numbers that occur there, and there's also these, like when every time you do a hook, there's a whole lot of stuff. It's really quite fascinating. So let's look at this. And I do want you to notice that we call these rows 0, 1, 2, 3, 4, 5, and then of course 6. And then I want you to look at this diagonal right there. And here, this diagonal, we always get the name of the row. So there was no number here, so we'll call that 0. That was the 0 row. Then this was row 1, row 2, row 3, row 4, etc. The diagonal just after the diagonal of ones, the next diagonal is the name of each row. So we're going to look now at one of the areas that we as mathematicians look at with this Pascal's triangle, and has to do with what is called a binomial expansion. So if you look at this column right here, you've got binomials, a plus b. And you have a plus b to the 0, a plus b to the first, a plus b to the second, third, fourth, fifth, and so forth. We keep raising 1 degree for each of these binomials. And if we were to expand them out, multiply them out, and see what we get, well, anything to the 0 power is just 1. Anything to the first power is just whatever it was. So a plus b to the first is just a plus b. But a plus b to the second, we get the first one squared and the last one squared and twice their product. If we go a plus b to the third, well, we would multiply by another a plus b, and here we get that, and we have all of these. And what I want us to concentrate on are the coefficients. So this is just the constant 1. Here we have the coefficients 1 and 1. So I'm going to now put in all of those coefficients in purple. We have 1 and 1, then we have 1, 2, 1, then 1, 3, 3, 1, then 1, 4, 6, 4, 1. And you think, oh, where have I seen this grouping before? Well, it came from, and I'm going to go back, it came from Pascal's triangle. Each one of these rows are the coefficients on each one of those binomial expansions. So this right here, those degrees, 0, 1, 2, 3, 4, 5, that is the nth degrees, or the whatever degree it is, tells us which row of the Pascal's triangle that we would use for coefficients. Now, the number of terms, when we multiply this out, a binomial expansion out, we look at this that we had to the 0 degree, there was 1 term. To the first degree, there were 2 terms. To the second degree, there's 3 terms. And so there's always 1 more term than the degree of the expansion. The first term is always, and you look at each one of those, it's always 1 times a to whatever the degree of the expansion was. So when we're squaring it, our first term is 1a squared. When we're raising it to the 5th power, our very first term is 1a to the 5th. So the first term is always 1, and then a to the n, whatever this a is. The last term is always 1b to the n. We're going to look at the exponents of a, and if we look at this, and it starts, let's look at the fifth row. It's 5, 4, 3, 2, 1, and then there's 0 a's. So what we do is we say, oh, it's whatever was the degree of the binomial expansion, and then it goes down by 1 all the way until we get to 0. That is called descending order. So it's always descending. The exponents descend from n all the way to 0. For the b's, if you look at the b's, and we'll go to the fifth row again, well, there's b to the 0, then b to the first, b to the second, b to the third, all the way to b to the n. And that is ascending order. So they ascend all the way from 0 to n. The sum of the exponents, so let's just go to the fifth row and let's look at this. We have a to the fourth degree and b to the first degree. If we add those 2 degrees, we get 5. So anytime you add the exponents of a and b, you get n. So let's expand this binomial. It says a plus b to the 6th degree. Well, we're going to do descending order for a's. So there they are. A to the 6th, a to the 5th, a to the 4th, a to the 3rd, it did all that. And I drew the Pascal's triangle here just to remind you so we don't have to keep going back. You've already got it on your paper and you have that 6th row that I asked you to write down. So here we have our a's in descending order. We have our b's in ascending order. There they are, they're ascending. So it's b to the 0, 1, 2, 3, 4, 5, all the way to 6. Then we're going to take this 6th row from Pascal's triangle and put those as coefficients. Oh, I forgot. I wanted to remind you that the degrees always add up to whatever the degree of the binomial was. This was a 6th degree, so all of those degrees for a and b add up to 6. Okay, we'll put all of our coefficients, and then we connect with addition. And that is the complete binomial expansion. Now, let's simplify it a little bit. A couple of these terms, the first term and the last term, well, these simplify. You've got b to the 0. We don't need to write that. We have a times 1. We don't need to write that. Same thing with our last term. We've got a 1 and an a to the 0. We don't need to write those. Additionally, I have, a to the first degree here, and I have a b to the first degree. I don't need to write the first degree. So I'm going to clean this up, and that is the way we would write it. We've got a to the 6th, which we know is 1, a to the 6th, b to 0, but we just write a to the 6th. And at the end, we have b to the 6th. And again, these ones that had a degree of 1, I just wrote them without the 1. All right, we're going to do expansion of x plus 2 to the 7th. So we have our 7th row. We could do it this way. I just did my 7th row, and now I have my descending order of the first term, x. I have my ascending order for the second term, which was 2. So I have all of that second term with the ascending degrees. I have my coefficients. I connect it with addition. So here we've done the expansion. Now we need to do some simplification. Again, anything to the 0 power we can just erase because that just means times 1. And the times 1 we don't need. The first degrees we can get rid of. But not only do we have that, but we have some multiplication to do. Here we have a coefficient of 7, and it's times 2 to the first. So that's going to be 7 times 2, which is going to give me 14. So we're going to clean this up, and we're going to multiply all of the numbers that we can. You can use your calculator and find the multiplication of each and every one of those terms. This next one, number 3, we're raising that to the 4th degree. So I'm just looking at the 4th row of Pascal's triangle. I have 2 terms, 3m and -1. We're going to take those terms, writing the first term in descending order. And then remember, this second term is not 1, it's -1. So I'm going to put it in parentheses. And I have it in ascending order, 0, 1, 2, 3, 4. There. And then I have the blue numbers for the coefficients that I connect with addition. Now we need to do simplification. -1 to the 0 is just 1. So this is just going to be 3 to the 4th m. Well, 3 to the 4th is 81. So we've got 81 m to the 4th. This next term, we've got 4 times 3 to the 3rd. So 4 times 27 times -1. And we're going to have -108. And then you're going to keep doing that with each one of these terms, simplifying it. Okay. So 4 and 5 and 6, you need to do those and post them to Google Classroom. And that is your homework assignment. And that's the whole lesson for today.